Welcome to Module 2 of Control Engineering. In this module, we will build on the foundations established earlier. We will discuss PID controllers, frequency response, Bode diagrams, gain and phase margins, and stability analysis in the frequency domain using the Nyquist criterion. We will also cover the practical side of control engineering, measurement techniques, sensors, instruments, error sources, noise filtering, and safety practices in laboratories. 2.1 The PID controller. One of the most widely used controllers in engineering is the PID controller, which stands for proportional, integral, and derivative. The proportional term reduces the error proportionally to its size. The integral term removes steady-state error by accumulating past errors. The derivative term predicts future error by analyzing the rate of change. When combined, these three actions provide flexible and effective control, making PID controllers suitable for everything from temperature regulation to motor speed control. 2.2 Frequency response and the Bode diagram. Frequency response analysis studies how a system reacts to inputs of different frequencies. The Bode diagram is a plot that shows the system's gain and phase shift as functions of frequency. It is an essential tool for analyzing stability and designing controllers. By examining the Bode plot, engineers can identify resonance frequencies, determine bandwidth, and evaluate gain and phase margins. 2.3 Gain and phase margins. Gain margin and phase margin are measures of how stable a system is. The gain margin tells us how much we can increase system gain before it becomes unstable. The phase margin tells us how much additional phase lag the system can tolerate before becoming unstable. These margins are critical in practical design because real systems always have uncertainties. Engineers ensure that adequate margins are built into the design to account for variation and disturbances. 2.4 Nyquist criterion and frequency domain stability. The Nyquist criterion is a graphical method for assessing system stability in the frequency domain. It considers both gain and phase shift across all frequencies and helps determine whether feedback will lead to stability or instability. This approach complements the time domain analysis we studied earlier, giving engineers multiple tools to assess system performance. 2.5 Basics of measurement techniques. Control engineering does not exist in theory alone, it requires accurate measurements of physical quantities. In the laboratory, engineers use instruments to measure voltage, current, displacement, temperature, and more. Key instruments include multimeters, which measure voltage, current, and resistance. Oscilloscopes, which display signal waveforms over time. Moving coil meters, which are analog devices for electrical measurement. Measurement devices can influence the system they measure, known as the load effect. Engineers must understand these effects to avoid distorted results. 2.6 Sampling, aliasing, and amplitude measurements. In digital control systems, signals are sampled at discrete time intervals. If the sampling rate is too low, aliasing occurs, where signals are misrepresented as lower frequencies. To prevent this, engineers apply filters before sampling. Amplitude measurements also matter. Engineers distinguish between peak values, peak-to-peak values, and RMS values. A true RMS meter provides an accurate measure of effective power, especially for non-sinusoidal signals. 2.7 Noise, error, and filtering. Every measurement is subject to error and noise. Errors may come from instrument limitations, environmental factors, or operator mistakes. Noise refers to unwanted random variations in the signal. Filtering techniques, both analog and digital, are used to reduce noise and improve signal quality. 2.8 The Wheatstone bridge and sensors. The Wheatstone bridge is a fundamental circuit for measuring resistance with high accuracy, and it forms the basis of many sensors, such as strain gauges. Sensors are essential in control systems, as they provide the feedback signals that controllers rely on. 2.9 Electrical safety and occupational safety. Finally, engineers must practice safety in laboratories and workplaces. Basic electrical safety includes avoiding direct contact with live circuits, using proper grounding, and respecting voltage and current limits. Occupational safety also covers personal protective equipment, safe handling of instruments, and adherence to regulations. Safety is not just a formality, it ensures that engineers can carry out measurements and experiments without harm. In this module, we studied practical tools and advanced concepts, PID controllers, frequency response analysis, Bode diagrams, gain and phase margins, and Nyquist stability. We also examined measurement techniques, sampling, aliasing, noise, error filtering, sensors, and safety practices. These topics prepare you not only to analyze and design control systems but also to implement them in the real world safely and effectively.